Hello, everyone. My name is Joe. I'm from NVIDIA Multimedia Hardware team. I'm glad to be here to share with you the NVIDIA RISC-V story. So these are the outlines of my story today. So first, I'm going to introduce you to the NVIDIA real-time Falcon CPU. Basically, our story is not to create a new core, which is the RISC-V based. Our story is about to replace existing NVIDIA embedded CPU with a new ISA, which is RISC-V based. I'm going to talk about why do we need a new CPU, why do we need a new architecture, a new ISA, and why do we believe RISC-V is the right direction for the next generation of the NVIDIA embedded CPU. And finally, I'm going to introduce the NV homemade RISC-V architecture we are developing for the next generation of NVIDIA SoCs. So this is a Falcon, an overview of NVIDIA Falcon processor. Falcon stands for Fast Logic Controller. It was actually introduced over 10 years ago and now used in over 15 or almost 20 different hardware engines today in all the NVIDIA products, including Tegra's and GPUs. So it was introduced back in a decade ago, about 12 years ago, as a front-end engine for the GPU. So basically, if you are familiar with GPU architecture, there will be a host to send methods down to the hardware engines, for example, video engines and graphics engines. The command streams are usually hard for the hardware engine to interpret. So we need a lightweight, programmable CPU to help process those methods and program hardware. And that's why we invented this Falcon CPU. The design target at that time was that because we needed in a lot of different hardware engines, it has to be highly configurable. So basically, everything other than the basic pipeline can be configured. So it can fit to multiple hardware engines. It has to be designed to fit to design for long memory latency, because in our GPU and Tegra SoCs, usually the memory latency between our hardware engine and our memory is pretty long. We're talking about 500 to 1,000 cycles of latency. And it has to be very low area. And also, the last, it has to be designed for security, because we want to prevent someone to run malicious code on this embedded CPU in order to hurt or do something bad to our GPUs. The diagram shows the architecture of this embedded CPU. As you can see, this is the pipeline. It has 6 stages, 16 GPR and 16 SPRs. The ISA is NVIDIA proprietary ISA. We have a variable length ISA, varies from 2 bytes to 6 bytes. Because of the memory latency, it was designed that all the code will be resident in its IRAM and DRAM, so we don't have a cache. It's very simple. We have a DMA engine here, and we have DMA instructions to move data between the main memory and the local IRAM and DRAM. As you can see on the bottom, there are some blocks that you can find from every normal embedded CPUs. There are interrupt controllers that can process interrupts. It can take external interrupts. And there's interfaces to host. Like I said, the main purpose of this CPU is to be the front-end controller of the engine. So it has to take commands from host. So we have host interfaces. On the left, we have the debug module, in-circuit debug module that can insert commands to the pipeline. You can stop the pipeline. You can step and you can jump. You can read the states of the processes. And we have a config bus that we can talk to the subunits of this controller. On the top, we have some special parts. Those are the crypto accelerators that adhere to the Falcon engines. We have high performance AES, SHA, and also ISA ECC. The whole purpose is we have them is that there are two reasons. First is that for some use cases, for example, in security engines, we need to accelerate the crypto algorithms, AES, SHA, or ISA. The other reason is that, as I mentioned, we need to protect the CPU from running any code other than NVIDIA signed U code. So these engines are used to validate the U code. Accordingly, the processor has different security modes. Basically, it has three security modes: non-secure, light secure, and heavy secure. In heavy secure, all the codes had to be signed. And the only way to run the heavy secure code is to load the code into IRAM and write the signature into a register, and you kick off. And then hardware will take off, do all the signature check. Once it passes, you'll drop into the heavy secure mode. Once it is in heavy secure mode, no one can read any register state from this register, even from host. So it guarantees that the processor is in a very secure state, that it can use keys. For example, it can handle the HTTP applications. While non-secure mode, you can still load U code and execute the core, but you cannot access most of its registers. Most of the registers will not be accessible in non-secure mode. While in light secure mode, it is a light model that with some systematic protection that allows only NVIDIA signed U code can run on this processor, but it still has a lot of other visibility so that software can easily debug this core. So this is the Falcon core we're using today. Then why we need the next generation of Falcon? So there are reasons for doing that. Like I mentioned in my last slides, this core is used in over 15 different places all over GPU and Tegra chips. There are many use cases. Some use cases are very simple, while there are new use cases that requiring more horsepower and feature from this simple embedded processor. The key requirements from our software team are including a very wide addressing range. They want to make this core like a central controller of the CPU as a GPU service processor. So it has to have a very wide addressing range. Our software team is asking for more than 50-bit native processing, and 64-bit is required in the near future. And obviously, we need more performance from that. But unfortunately, Falcon was not designed for performance in the first day. As you can see, the performance is pretty poor. It's about 0.7 DMIPS and 1.4 core mark. So it definitely cannot meet the requirement from the new use cases. And I mentioned that the Falcon does not have has a D-cache because everything you have to load the code and data into its local memory and execute them, and try to avoid swapping data between its local memory and GPU or Tegra memory subsystem. But the new use cases does not want to bound to the memory limit. They want a more powerful I-cache and D-cache. The last one is rich OS support. Although Falcon has different security levels, it does not have a privilege instruction adhered to that to support the rich OS of RTOS. So those are all the requirements coming from the software team that the old processor we're using today cannot meet. So we are thinking about moving to a more powerful embedded CPU that can meet all the new requirements. That's why we're thinking moving Falcon, this small processor, to a new next generation that with more features and more powerful performance. So the options we have, obviously, two major options, buy or build. We have a lot of companies building amazing CPUs like ARM. They have A family, R family. We have Synopsys, Arc, which is also very good. We have MIPS and Cadence. And for build, we can either improve the Falcon or we can move to a new ISA. And this is when RISC-V come into the picture. Basically, we evaluated all the options against our key requirements and see if any one of them can meet all our requirements. We compare all the CPUs. Our key requirements, including core performance, we require at least a 2x performance out from the new CPU versus today's Falcon. So area-wise, it needs to be very small, and it needs to have a security model. And because of the large memory latency, it needs to have a tightly coupled memory that some critical code can be executed from that. And it needs to have a cache, and the addressing has to be 64-bit. And the ISA, it's strongly preferred to be extensible because we perhaps need to optimize the ISA to be able to accelerate some certain use cases. And it has to be support safety with ECC or parity. And for software development, we need a functional simulation model that we prefer to be a system C based. So we compare, basically we compare ARMS and Synopsys HS, and we select RISC-V rocket chip to compare. And we build a simulation model for the next generation of Falcon and see how much effort do we need to pay in order to improve the Falcon ISA or architecture to meet the requirement. For ARM processors, obviously A53 is listed here just for it has 64-bit. The area is obviously too big for an embedded processor. The other cores from ARM, they all has different features, but they cannot meet all our requirements. For example, A9 does not, the area is too big, does not have a TCM. R5 has TCM, but does not have a security model. The addressing mode is not 64-bit. And Synopsys HS also no 64-bit. While the Rocky Core, although it does not have a TCM and it does not have a functional simulation model, it has a cycle-based C++ model. But we think that it is not a drawback of the ISA. It depends on the implementation. So after the comparison, also there's another factor that all the cores from ARM are very, very expensive. And especially when you are trying to build a core from ARM ISA, well, that's more expensive. So we concluded that RISC-V is the right direction to the next generation of ISA for our homemade embedded processor. And we decided that we will build our own implementation of RISC-V core. Next, I'm going to introduce the NVIDIA RISC-V architecture. This is a summary of a comparison of our old architecture and new architecture, which is RISC-V based. So basically, the first generation of NV-RISCV will be very similar to the Rocky Core. It is in order issue machine. It has an out-of-order execution in order write back. It has an ROB. It has an ID cache. It has a prediction, but it does not have a FPU. It does not have a MMU as well because we like to make it simple in the first generation. We didn't take the Rocky Core because it does not fit to NVIDIA development environment very well. This is how we imagine this core will work. Because the area is very small, it will be plugged in to the original core as a second core. We see two benefits from doing that. First is we can provide very good back compatibility on interface. It is easy to integrate for the engines that are already using Falcon today. They have a lot of tests running with Falcon. So replacing the core will cause a lot of effort for them. So we introduced the core as a second core. You can share all the subunits with Falcon. You can share the ITCM and DTCM with Falcon, but the RISC-V core has its own cache. And the other reason is that we want all the security tasks to still run in Falcon, at least in first generation, while leverage the non-security applications, all the compute-intensive applications to the new RISC-V core. With that, the security task and non-security task or light security task are perfectly isolated. So the risk for security exposure is less. This is the table compares the Falcon rocket chip, NV-RISCV, and Boom. I think the Boom data may not be up to date, but as you can see, the Drystone scores and the Cormac, the NV-RISCV, the first generation of our processor is very similar to the rocket chip. While we run in a very higher frequency, the core we developed can run. We are targeting to run on 1.5 gigahertz under 16 nanometer. And the area we are projecting is about the synthesis. This is a pre-layout area. It's about 0.05 to 0.06, so it can be added into the original Falcon core without much of area concern. As I mentioned, we had an environment that with very big memory latency, so we did a lot of optimizations to our cache to tolerate the large latency. So first, the cache, as always, it is configurable in size, cache size, LAN size, associativity, and write policy. The optimizations we're doing, including store buffer, write merging that merge all the small writes. We had the line view buffer. We had a VTIM buffer as well, stream buffer to prefetch next line for the code. We are planning to do a software prefetching in the future, and also we are planning for L2 in the future. It really depends on the area and the performance of the first generation. We can only measure them after tape out and software use them. So at least in first generation, we don't want to bring in L2 because of the area. And we are thinking about the banked cache as well. And obviously, we have ITCM and DTCM. We use our, we write a small benchmark to stress the cache. Basically, it's a D tree that creates 8K nodes and randomly insert, modify, and remove nodes to measure our cache performance. The performance is measured by the cycles of execution cycles, so less is better. On the right end, this bar is that assuming all the code and data is resident in local memory, so it's a perfect number that you cannot achieve, but this is a target. This is an original RISC-V core without any cache optimization. This is the Falcon. We write a simulator and we try to simulate the cache with all the simulation optimizations we do and simulate its performance. And we also simulate the RISC-V with the optimized cache. As you can see in the diagram, the cache performance can be greatly improved. We can achieve 2x. The cycles of execution cycles can be reduced to up to 50% after the optimizations. This slide shows the area of interest to NVIDIA that we would like to work with the community and we like to contribute, or we like to work with the community to make some progress. The first is the toolchain. We're interested in toolchain for automotive because we are entering the automotive market. We are interested to have a toolchain that can meet automotive standards such as ISO 26262, ISO D standard. We are also trying to make tools to debug, that is to debug your code on both silicon, FPGA, or emulator. We need tools for performance tuning as well, because as I mentioned, some use cases are very critical. We need to understand what is the hotspot and how can we build a better or extend the ESA to achieve more performance. So we need a performance tuning tool to understand which part of the code is burning the most time. And the last, we are thinking about tools for flexibility that users can easily customize the ISA. For example, once you add the ISA, the tool can be built and auto-release something that is ready to use. Finally, we are also interested in compiler options like ILP 32, ILP 64, because not all the use cases are requiring 64-bit full addressing range. So it would be better to have a 32-bit pointer, so the data size can be reduced. That can achieve better cache performance. On security side, we are thinking about adding crypto instruction or more crypto extensions. As I mentioned, security is an important use case for today's Falcon. So once we replace the Falcons with RISC-V, security will be a very important part for the RISC-V as well. So we will see if we can add some crypto instructions to that. And we may need more instructions such as cache instruction, for example, prefetch, invalidate, flush, etc., to further optimize our cache performance. Okay, this is a conclusion. First, the Falcon is the NVIDIA proprietary control processor, and new use cases require more feature and performance from that Falcon processor. It is hard to improve the current CPU and ISA to meet all the requirements. This we evaluate different options in the market, and the results show that RISC-V is the overall best choice as next generation of Falcon. Finally, we'll build a new core from the RISC-V ISA. Okay, that's all. Thank you.
All right, thanks, Joe. Do we have questions for Joe?
Hi, Dave Patterson from UC Berkeley. I was interested, why did you want to design your own core versus use a core?
Because, like I said, we evaluate all the options.
But the expense of designing your own core wasn't an obstacle for you to do it?
We don't need a core that's that expensive, and we think designing a new core is affordable.
And how much was cost of getting somebody else's design not an issue for you?
Cost, area, and addressing like 64-bit addressing.
But was it just a technical decision to go with RISC-V rather than the business cost of the...
It's both.
Both?
Honestly, yeah.
Rishir Nikhil from BlueSpec. In your table of features, yes/no comparisons of various architectures, under RISC-V you said no functional simulator, but I'm not sure I understand, because Spike is a functional simulator for RISC-V. It's not a simulator for a particular architecture or anything like that, it's for the ISA, but I'm not sure I understand what you mean by no functional simulator.
We want a transactional functional simulator. Preferably System C based or something like that. I'm not sure I understand your question.
Well, Spike is a C++ program that simulates completely the RISC-V ISA, and I think of that as a functional simulator.
On that aspect, I think yes. Yeah.
All right, thank you, Joe.